Hi everyone. In this video we will learn about periodic properties. We talked about it earlier on that elements show a trend in their properties as they go down the group or across the period. So we learned earlier on that there are different groups, and groups are also called families. We have alkali metals, alkaline earth metals, transition metals, noble gases, halogens, chalcogens, pnictogens. But when it comes to their physical properties, which is what I will talk about right now, no matter which family they belong to, they show a trend going down the group and going across the period. So there are certain physical properties that I will discuss in this video, and the list of those properties is right here. We'll talk about ionization energy, electronegativity, electron affinity, atomic radius, and ionic radius. And we will talk about the trend of these properties across the period or down the group. In the list of these properties, although ionization energy is listed first, but I would like to talk about atomic radius. Because I personally think that if you understand the atomic radius, it makes it easier to understand rest of the properties and their trend and how it works. So let's talk about atomic radius. Before I mention the trend, we need to understand what is radius. Radii means size. I'm sure you understand the radius of a circle. That is the distance from the center to the, outside. This is called radius of a circle. So if we want to bring this knowledge into the atom, according to Bohr, there is a nucleus, and the one electron of hydrogen atom is revolving around the nucleus in an energy level. So if we talk about Bohr, then Bohr did define the boundaries of the atom. So Bohr said that if this is the nucleus, this is the boundary line of the atom, and this is where the electron is revolving. But we know that hydrogen is, first of all, hydrogen is the simplest atom you can talk about. And beside that, based on the atomic model that we know today, which is the quantum mechanical model, we cannot really define boundaries of the atom because we don't believe what Bohr said that they are orbits. We don't believe in orbits anymore. We think that electrons are constantly moving and they're changing their paths. I cannot really draw the line that this is exactly where the electron would be. Yes, we can say that this is the region where there is maximum probability of finding the electron, and we call that region to be orbit. So yes, we can say that within that orbit there is a maximum probability of finding the electron, but we cannot say that this is exactly where it will be, or we could draw a line or calculate the radius. So keeping that in mind, bottom line is that when it comes to the atom, it is hard to define the boundaries of the atom, and it is hard to calculate the radius. So then what is the solution? The solution is that instead of calculating the radius of one atom, and defining the boundaries, which I cannot, we will talk about diatomic elements, the covalent elements. So I have, let's say, a bromine and a bromine, and I will bond them together. So if I have two bonded bromine atoms, what we will do is we will calculate the distance between one nucleus to the other nucleus. Because since they're bonded together, so this distance is given. It will not change. So this will be called as the bonded radius. Okay, so I will call it bonded radius. If I'm calculating the radius of only one atom, that will be called non-bonding radius. So it's hard for us to calculate non-bonding radius. So what we do is we calculate the bonding radius. So the bonding radius is the whole distance between the two nuclei. So to calculate the individual radius for the element, I will do half of the bonding radius. Okay, so I'm going to use this equation to calculate it. That hold on. To calculate the bonding radius, I just wrote the other way around. To calculate the bonding radius, I will do half of the total distance. So this is the total distance between the two nucleus, and half of that distance will be the bonding radius. So this way I can calculate individual atoms. This is the best we can reach to, and you can calculate. You can get this information in your data booklet, in your IB data booklet. In section 9. In section 9, you will find the covalent atomic radii of the element. So this is called, in general term, the atomic radius. For example, the radius of, if I want to find out the radius of bromine and fullerene, your data booklet will tell you that the atomic radius of bromine is 117 picometers. We will do it in picometers. The atomic radius of fullerene is 60 picometer. So what should be the atomic radius of bromine fluoride? Well, you add them together, it will be 177 picometers. So this kind of information is given in your data booklet. Okay, and again, as I'm explaining, that the atomic radius cannot be calculated individually. It will be calculated as a bonded atoms. So the example that I'm giving you here is for the covalent compounds. So this example I gave you is for the covalent molecules. I should say not compounds, or molecules or compounds. So I can do it for chlorine, and I can see the distance between the two and then divide it into half. But what do I do if I have metals? So I can do the same thing for the metallic compounds, but in the case of metallic compounds, we will assume that metals are kind of loosely bonded together, by the metallic, by their valence electrons. So I assume that if there are two metals, they are in a crystal lattice. So, so in the crystal lattice, whatever the distance is between the two nuclei, that will be the distance for my, bonded radius. So, and for the gaseous atoms, I will say, okay, they come close together. So this is a gas atom here, and this is here. So the valence electrons of this and valence electrons of this are kind of holding each other by van der Waals forces. Okay, van der Waals forces. So it will not be as accurate as it is for a covalent compound, because they're constantly moving and they are very lightly or held together. But this is the best I can get. So we call it actually the van der Waals radius. There is a term that we use is the van der Waals radius, because we are using this force to calculate the distance between the two nuclei. So again, what I'm explaining here is that we are calculating bonding radius and then divide it by into half to calculate the non-bonding radius. Okay, so if you see these terms, you should be able to understand what these are. So this is the distance between the two nuclei. This is the bonding radius. This is the non-bonding radius. And there are different kind of, logics that we are using, I should say, to calculate it for different molecules. For covalent compounds, we have a very strictly, covalent is the easiest one because we have a very strong bond that is holding them together. So this distance will not change. But for metals, we calculate it from the crystal lattice. From the gases, we calculate it from the van der Waals forces. Anyway, but once we know the radius, what we really need to know is that what happens to the radius as we go across or go down the group. So the radius increases on going down the group because electrons are added further from the nucleus. So there is less attraction between the nucleus and the outermost energy level. Okay, but there is another term that is being used. It's called shielding effect. So let me explain what the shielding effect is. That if you have a nucleus and let's say you have 8 protons in it, and then you have electrons here, so you have 2, and then so the number of electrons that are between the nucleus and the outermost electrons, which here is only 2, are called 4 electrons. Okay, so the nucleus is, as you know, is positively charged, and this positively charged nucleus is pulling the negatively charged electrons towards itself. So this positively charged nucleus is kind of trying to attract the valence electrons that are sitting right here. But more electrons that you have in between of the nucleus and the outermost energy level, the less the effect will be, because that attraction will be balanced out by the by the inner electrons that are between the nucleus and the outermost energy level. So those core electrons or the inner electrons are creating something that is called shielding effect or screening effect. It is on your page number 77 in the book, in your actual textbook. Shielding effect or screening effect. So, but again, what is the shielding effect? It means the number of electrons that are present between the nucleus and the valence electrons. These are the valence electrons. So the number of electrons that are present between the nucleus and the valence electrons, they kind of balance out the attraction that is from this nucleus to the electron. So there is less attraction for that. The more the electrons are here, the less the attraction or bondage will be. Okay, so that is called shielding effect. So going back to it, what I was explaining, that as we go down the group, the atomic radius increases. And why does it increase? If you look at the periodic table, hydrogen is in period 1. That means hydrogen has only one energy level. Now lithium is in period 2. That means lithium has two energy levels. Okay, sodium is in period 3. That means it has three energy levels. So I don't think I have to explain it any further, that as we go down the group, since we are adding another energy level, the atomic radius increases. Okay, as we go down the group, the atomic radius increases because we are adding more and more energy levels and we are adding more electrons in it. When we are adding more electrons in between, the nucleus cannot really pull the electrons that are sitting outside towards it. So the nuclear charge weakens. So since nuclear charge decreases, the atom will get bigger in size. So there is less hold of this nucleus on these outer electrons. So there's less attractive forces. On the other hand, if we go across the period, as we go from, let's say, sodium all the way down to neon, we are adding more and more protons inside the nucleus. We are adding more protons to the nucleus, which means the nuclear charge is increasing, whereas the valence shell does not increase. You still have three energy levels, no matter you are on this side of the periodic table, or let's talk about chlorine, which is on the other side of the periodic table. You still have only three energy levels. Okay, but what happens is that this one has 11 protons in the nucleus, this one has 17 protons in the nucleus. So this nucleus is much more powerful compared to the sodium nucleus. So this nucleus has more power to pull the electrons inside. So the nuclear charge increases. So once the nuclear charge increases, it pulls the electrons inside, so atom will shrink. All right. So going back to the slide, in general, as a summary, the atomic radius will increase down the group and it will decrease across the period. Okay, let me see if I can show you a picture of it. So as you see here, so I was talking about sodium and chlorine. So sodium has this atomic nucleus, and as you go across, the size gets smaller and smaller. And the reason I'm telling you is because the number of energy levels does not increase, within the same period. They're all in the period 3. But we are adding more protons to the nucleus, so the nuclear charge is increasing. And that pulls the electrons inside. So each added electron feels a greater and greater nuclear charge because the protons are pulling in the same direction, instead of scattering it, instead of electrons being scattered away. So and these values are in nanometers. Okay, so this is 0.186 nanometer and this is 0.099 nanometer. So you will see how much of a difference it creates. So you need to know in general the trend of the atomic radius, that atomic size gets bigger down and gets smaller across. We call it a snowman effect, So it's going down, it gets bigger, and going across, it gets smaller. So here is another picture of it on a bigger scale. You will see that as you go down, it's getting bigger, and as you go across, it's getting smaller. If you still have any questions, let me know, and we can talk about it in class. Let's talk about the trend of atomic radius of ions, instead of atoms. Earlier on, what I was talking about was the atoms. So before I show you this picture, what if we talk about the sodium atom? So sodium atom has 11 protons and 11 electrons. And if we do the diagram, you have 2 electrons right here. 2, 4, 6, 8, and this makes it 11. So when sodium becomes sodium positive 1, what is supposed to happen? It is supposed to lose an electron. And when it loses an electron, let's see what's left. So 2 electrons here, and 2, 4, 6, and 8. So this is what is left. So this is sodium ion, and this is sodium atom. I don't think you need any explanation of what happened to the size. You see that the atomic size gets smaller as we go from atom to a cation. So all of the cations are smaller in size compared to their atoms because they have lost this electron and the energy level is gone. And once that electron is gone, their nuclear charge, you have more protons than electrons. So since you have more protons than electrons, they have more power to pull the electrons inside, the rest of the electrons inside. So that will decrease the number of the size of the atom. So on the other hand, for anions, chlorine has again 3 energy levels, and chlorine ion will also be 3 energy levels. As a matter of fact, you have 7 valence electrons right here, but for the ions it will be 8 valence electrons, because it's going to gain an electron. So this is the chlorine atom and this is the chlorine ion. So since you gain the electrons, these electrons have more power to work against the nuclear charge. So they will repel each other, so more electrons repel each other. So the size of the chlorine atom is smaller compared to the size of the chloride ion. Okay, so all of the anions get bigger in size, okay, compared to their atoms, whereas all of the cations are smaller in size compared to their atoms. So let's talk about, you see here, all of the metals are smaller in size, whereas the non-metals are larger in size. So as we know in the periodic table, I hope I don't have to explain that in detail, that we have, this is the periodic table. We have metals on this side, non-metals on this side. All of the metals, they lose electrons and make cations. All of the non-metals gain electrons and make anions. So all of the metals, when they lose electrons, their cations will be smaller in size, and non-metals, their anions will be larger in size. So this is the atomic radius trend of atoms as well as ions. So it's explaining you the same thing that I have drawn before. So you see here the size of the lithium atom is much bigger than the size of the lithium ion. This is in nanometers. You have 0.152 nanometer versus 0.078 nanometer. So it's a huge difference. So cations are smaller than the atoms from which they came from. So the electron proton attraction has gone up, and so the radius decreases. You have more protons to pull the electrons inside. So that is the thing. And here is another, same thing over and over: lithium versus lithium ion, sodium atom versus sodium ion, potassium atom versus potassium ion. And then anions are larger in size compared to their atoms, and the same story again. Because you added more electrons, and that increases the repulsion of electrons to make the size bigger. And you see there's a huge difference between the sizes of the atom versus the size of the ion. Okay, so these are the ionic sizes. This is again the comparison of fluorine, chlorine, bromine, iodine, the atomic size versus the ionic size. So this is the chloride ion, much bigger than the chlorine atom. This is bromide ion versus bromine atom. So atomic and ionic radius. Okay. So isoelectronic ions means when you lose or gain electrons, they get same number of electrons. I mean, when any element lose or gain electrons, they become same number. Like for example, let's talk about oxygen. So if we talk about oxygen, oxygen has 8 electrons. So when oxygen gains 2, it has now 10 electrons. So fluorine has 9. When it gains 1, it has 10 electrons. Sodium has 11. When it loses 1, it has 10 electrons. So these are called isoelectronic, because they have same number of electrons. These are different elements, but by gaining or losing electrons, now they have same number of electrons left in their ion. So you see that the isoelectronic ions have the same number. The more negative an ion is, the larger it is. So if you have this one is bigger than this one because it has more electrons on it. Okay, so the less electrons it has, the smaller it is. So aluminum is the smallest one because it has lost maximum number of electrons. So more electrons any element loses, the smaller the size it's gonna get. More electrons any atom gains, to become an ion, the larger the size it's going to get. So this is the summary of the whole thing, but we have only talked about atomic radius so far. So we will come back to it later on. Let's from here on we will go to the ionization energy, because that is a trend that is, hold on one second. So ionization energy is the energy to remove an electron from the, okay, what's happened to this? Alright, so let's talk about ionization energy. Ionization energy is the energy required to remove an electron from the atom. Okay, and ionization is energy required to remove an electron from an atom. So which electrons are we going to remove? Of course, from the metals. Metals lose electrons compared to more easily than non-metals, and non-metals lose electron with much more difficulty. So the one that can easily lose electron, of course, I will spend less energy, whereas the one that is hard to take the electron out of, I would have to spend more energy. So it's pretty common sense. So ionization energy increases across the period and it decreases down the group. And why does that happen? Because we talked about the radius. So if this is the nucleus and this is the electron, and I want to pull this electron out, this nucleus is holding the electron very tightly because it is sitting very close to it. So the smaller the size is, it's more energy I have to spend to pull the electron out. Whereas if I have francium, francium has 7 energy levels, 3, 4, 5, 6, maybe 7 energy levels. So the nucleus is sitting right here. If I have to pull the electron out of here, common sense is that this nucleus of francium does not have much control over this electron, because it's a lot of shielding effect in between. Because a lot of inner electrons are balancing the, the charge, the nuclear charge. So this nucleus does not have much control over it. So I can easily pull the electron out. Okay, so hydrogen is here, lithium is here, and francium is here in the group. So as I go down the group, I would have to spend more energy here and least amount of energy here. So ionization energy decreases as we go down the group, because atomic radius increases as we go down the group. So since atomic radius increases, it's easier for me to take the electron out because of the shielding effect. On the other hand, as we know that the atomic radius decreases across the period. So if atomic radius is decreasing across the period, the nucleus is holding the atom electron, the outermost electron, very tightly. So it will be hard for me to pull the electron out. So long story short, that ionization energy is going to increase down the group and decrease across the period. And the reason for that is atomic radius. Atomic radius increases down and decreases across. I'm sorry, it decreases down and increases across. So it's opposite to the ionization energy. So, and the other one is the shielding effect. Okay, shielding effect works just like atomic radius. It gets smaller down and bigger across. So ionization energy gets smaller down. So I will spend less energy to pull the electron here compared to here. I will spend much more energy to pull the electron here compared to here. So ionization energy increases. Okay, I want to make sure there's no confusion. And it decreases down. And no, it's also not only ionization energies like this. There is first ionization energy, there is second ionization energy, third ionization energy. What that means is that if magnesium has two valence electrons, magnesium has two valence electrons, then once I spend the energy to pull one electron out, okay, that's called first ionization energy. When I take the first electron out, magnesium becomes +1. So the nucleus of the magnesium goes on high alert mode, that electrons are being pulled out. So it holds, the number of protons increases already because one electron is out. So when number of proton increases, it holds the electrons even stronger. So the second ionization energy is twice as much, sometimes even more, compared to the first ionization energy. And going to the third ionization energy is even more. So as I go from first to second to third ionization energy, the amount of the energy increases. Okay, and again, the reasons I've been telling you, the reasons are the shielding effect and the atomic radius. So we must understand the first ionization energy is much less than the second ionization energy, which is much less than the third ionization energy. All right, so, and again, the overall trend of the ionization energy is that ionization energy increases down and decreases across. So, again, highest on the top of the group decreases as the size of the atom increases. The results from the effect known as the shielding effect, because there are more electrons between the nucleus and the valence shell. So here is the representative groups. The representative groups are group 1, 2, and then 13, 14, 15, 16, 17, and 18 in the periodic table. They are called representative groups. So this is a trend for the representative groups, that it is decreasing down and it is increasing across. Sometimes it kind of varies, it's not always as simple as I'm explaining. There are a lot of exceptions, and that are because of the individual metallic properties of the elements. Here is another way that going across the period, from potassium to argon, the ionization energy will increase. Okay, going the other way around, it remains the same. So sometimes it remains the same, and across the period it increases, and going down the group it decreases. So you have helium, and then you have lithium. So you can look at it. Most of the time you are given this graph to understand the ionization energy. The next thing we want to talk about is electronegativity. Electronegativity is the force or ability of an atom to pull the bonded electrons towards itself. So let's say you have hydrogen and hydrogen, and they are bonded together. Okay, when hydrogen and hydrogen are bonded together, okay, there is one proton in this hydrogen, there is one proton in this hydrogen, and these are the electrons, the two electrons that are being shared from both sides. So this proton is pulling the electrons on this side, this proton is pulling the electrons on this side. It's tug of a war. But since the power is the same on both sides, the electrons will be equally shared between the two atoms. On the other hand, if I have hydrogen atom versus chlorine atom, which has 17 protons, and then I'm sharing the electrons, so there are 17 protons pulling the electrons on this side versus one proton pulling the electrons on this side. So it's like tug of a war thing. So common sense that the electrons will kind of lean towards chlorine, instead of staying in the center. They will lean on chlorine. And since electrons are negative, so when they lean on chlorine, they give a partial negative charge to chlorine and partial positive charge to hydrogen. But anyway, the force by which they are pulling the electrons towards itself is called electronegativity. Electronegativity has the same trend as the ionization energy, and the reason is also the same. The smaller the radius is, this chlorine has smaller radius, so the smaller the radius is, the more power it has to pull the electrons towards itself, because nucleus is very close to the electrons. A bigger the size is, if I have this big of a radius versus this big of a radius, so the smaller radius has more pull, has the ability to pull the electrons towards itself versus a nucleus that is sitting far away from these electrons. So this nucleus will have weaker, okay, weaker force to pull it compared to this nucleus which is sitting so close to the electrons. So the smaller the size is, the higher the electronegativity is. The larger the size is, the less the electronegativity is. So again, the same trend as of ionization energy, that for electronegativity, okay, it decreases down and it increases across. The most electronegative element on the periodic table is fluorine. Okay, we don't talk about group 18 because electronegativity is the energy or ability to pull the bonded electrons. Okay, group 18 don't bond. All right, inert gases do not bond. So we do not talk about electronegativity of 18. We're going to stop at group 17. So fluorine is the most electronegative element on the periodic table. It has electronegativity of 4, all right, versus all other elements. So I am sure in your data booklet you will be given the electronegativity charge and the values of the values of electronegativity. So you can see that how it increases or decreases. The other trend, in general, so what have we learned so far is that electronegativity and ionization energy have the same trend. They decrease down and they increase across. And they're opposite to the radius. Okay, the radius, it gets bigger down and smaller across, and same as the shielding effect. So the radius and shielding effect have the same trend, and electronegativity and ionization energy have the same trend. The other trend I want to talk about is electron affinity. So let's go to electron affinity. So you can read through these, slides, but I have already given you the explanation for all this. So as you see, this is the table that I was talking about, that it gives you the electronegativity values. So you see the electronegativity value is decreasing down, and you see the electronegativity value is increasing across. Okay, and as I was explaining, that fluorine is the most electronegative element on the periodic table. So it has the maximum ability to pull the electrons over. And you see that most of these nonmetals have high electronegativity versus the metals. And this is the electronegativity of hydrogen. So this chart is always given to you. So again, it decreases down and it increases across. You see some exceptions here or there. The next thing I want to talk about is electron affinity. Electron affinity is the energy that you need to add an electron, or I would say to take the electron out. Like chlorine has gained an electron and you want to pull that electron back out. So that has the same kind of trend. You see that it gets smaller down and it gets bigger across. Okay, so it is not going to be used much in the trends. It is just a general thing. You need to know how it works, but not necessarily you will get a lot of questions on electron affinity. But something we definitely need to learn is ionization energy and electronegativity. So electron affinity, we call it electron affinity, so this is the energy required to detach an electron from a singly charged negative ion. So if I want to detach this electron that has been a charge to it, that is called electronegativity. So a more common and equivalent definition is that the electron affinity is the energy released when one electron is attached. Okay, and we calculate it in kilojoules per mole. So all this is given to you is in kilojoules per mole. And the value of it, as you see, is increasing as we go across and go down the group. So the next thing we want to talk about, again, these are the trends of electron affinity and atomic number. And shielding effect I have already explained. So I believe this is about it. So we can go down and talk about the summary of it. For some reason this has stopped working. So let's talk about in general the summary of all of the trends that I talked about in this video. Here it is. Okay, so periodic trends. All right, so this is the periodic table. As you see, that the atomic radius will decrease across, okay, and atomic radius will increase down. Shielding effect, it does not change across, and shielding effect increases down. Okay, whereas electronegativity and ionization energy, they are opposite to the radius. So if radius is decreasing across, they both will increase. And if radius is increasing across, the electronegativity and ionization energy, they both will decrease. So this is a general trend that you need to know. And if you have any questions, please feel free to ask me in the class. Thank you very much for your attention.